Hmm. Okay, so we focus on the problem of exact nearest neighbor search, where we have given endpoints in d-dimensional space, and we have given a query object online. So basically, we have given endpoints in d-dimensional space, and we can store in some data structure or the way we want. And we have given a query object Q, which is again a point in d-dimensional space that may or may not belong to this dataset X. And our aim is to find the object in the dataset that is most similar to Q. Right? So this is the problem of our exact nearest neighbor search. So now we'll see we'll see some standard algorithm for this problem. So exact nearest neighbor search for Euclidean distance when we compute similarity or distance based on the Euclidean distance between the real valued vector. Okay, so can you suggest any algorithm for this problem? What could be the most naive approach to solve this problem?
So it will, we have to compare each
K
other.
Yeah, sorry?
KNN.
Uh, can you repeat? I didn't get you.
Sir, KNN?
How Canon will help here?
Like matching all the points with the other points, calculating the distance and finding the nearest neighbors.
Okay, so basically we take the query point and compute the distance with all the points in our data set and report the closest one.
Yeah.
Right? So that is linear scan, linear search, not KNN. So that is correct. So this is linear, basically linear scan. Compare the query item with every point in the data set. And what will be the time to find the closest element?
N square.
Not n square. Basically, you are comparing with everyone. So it will be order dn. Right?
What is D here?
D is the dimension. Basically, you need to compute the distance of query point with all the points in the data set. To compute a distance between, so suppose you have, this is your query point in D dimension. And suppose this is another point, say maybe xi, it is in D dimension. So we compute the distance between Q and X. Right? So its complexity will be order D. And we need to do it for all the points in the data set. So that's why its time complexity will be order Dn. Right? Right? And the space will be again order Dn because we need to have access to all the points. That will be the space. Another kind of approach. There are multiple approach, but I'm just stating the two possible straightforward approach. Another approach is indexing. So here basically we do kind of some sophisticated partition of space. So this is via Voronoi partition. I'm just stating the term. I'll not go in detail of this Voronoi partitioning. Right? So using which we can basically design a sophisticated data structure so that our query time is faster, right? So here the space required will be n raised to power order d, but the running time is faster. It's order d log n. So it's an improvement from n to log n, but at the cost of space. Earlier we require order dn space for linear scan, but for full indexing it is n raised to power order d. And so this thing is this full indexing approach is feasible only when d is small, right? Like, so d is say 1, 2, or maybe 3, right? Right. So is this point clear?
Sir, can you explain like how will be the spaces n to the power order of t? I mean, just in few lines. Okay. Thoughts.
So here you can think of we do space partitioning. We given a data set, we partition the space so that basically similar points uh, belong to the same partition. And now once we get the query point, we'll see in which partition query points falls, and we need to search only on that partition. So that's how this thing is happening. But this is somewhat very different to what we are doing. So I'll not go in much detail. But you can think of this is kind of a state for like kind of standard algorithm for exact nearest neighbor search that runs in time order d log n and requires space n raised to power order d. Okay, so now what should we do? So in exact nearest neighbor search problem, either the query time is linear in the number of data points, then space is somewhat controlled. But if you want to get faster algorithm, then the space complexity is very high. And this is called as phenomena of curse of dimensionality. Like with increase of dimension, basically the algorithms can be, the complexity of algorithm could be very high. Okay. So now what we'll do, we'll relax the problem. So basically we allow to have some tolerable error in the result of the algorithm, and we'll see if we can get a better algorithm than linear search, right? So for that, we'll first define approximate similarity search. So this is okay. So accordingly, we'll define.
Sir, here locality of LSH also will be
So we'll
similar.
use first. So we started with exact nearest neighbor search problem. We saw that okay, this getting exact nearest neighbor search problem is cumbersome, either due to the time complexity or time complexity of linear scan, or maybe space complexity of indexing based algorithm. Then what we are doing, we are relaxing the problem, and so basically we'll allow some error in our result, tolerable error in our result. So that is approximate nearest neighbor problem, and then we'll see how locality sensitive hashing can be used to give an efficient solution for approximate nearest neighbor search problem. So this is the agenda of today's class.
Thank you,
Okay.
sir.
Okay, so so here the problem statement is, so I'll state approximate nearest neighbor. So here again we have given a set X of data points and an accuracy parameter epsilon. So these two things are given to us beforehand, offline, right? So now using this, we can basically pre-process our input points, and the constraint is that and we have given query object q at the query time, right? So here basically the setting is we have given our data set and some parameter, and now using that we can pre-process our input the way we want. And the constraint is that when at the runtime we have given these query points, and then our aim is to find the point which is most similar to the query point in the data set X, right? Okay, so here as there is this accuracy parameter epsilon will, so this is somehow captures the error that we can allow in the result of the algorithm. So what we need to find an object Z from X that is most similar to Q, such that distance of Q to Z. So here distance could be like the similarity measures or distance measure that we are considering, Euclidean distance, dot product, cosine similarity, and so on, should be at most 1 plus epsilon times distance of Q to X for all point X in X. Right? So for example, so these are our data points, and suppose say this is Q, so this is Q. So suppose this is it's a point maybe X1 closest to Q, but so this is say so this is the point that is closest to Q, but our algorithm can, so suppose this is so this is 1 plus epsilon times, for example, comma Q1, and suppose there are say some point here, some point here, some point here, then algorithm can output either this point or this point, right? Right. So is the setting clear? Right. So if it is clear, you can say yes, so that we can proceed. If it
So
is not, then
just 1 second.
okay. So maybe I'll
No,
just
just that diagram. Only the diagram should be enough.
yes, 1 second. So I'll just clean it up. Okay. So this is said. So this you can think of radius of distance x1 comma q into 1 plus epsilon times. Okay, so basically the thing is, so suppose x1 is the closest item, closest data point to q. So algorithm can output any point that is within the radius of this distance of x1 to q into 1 plus epsilon. Right. So suppose if these 2 points are there in that radius, then algorithm can output either of these. That should be fine. So in a way, you can think of the algorithm is not outputting the closest one, but outputting a point which is, say, not uh, not far from 1 plus epsilon times uh, the distance to the closest point. Right. So is this point clear?
And epsilon is a positive value.
Epsilon is a parameter. So epsilon is greater than 1, you can think of. Greater than 0. Right. So is the setting clear?
Yes, sir.
Okay. So basically, in basically layman term, the algorithm can output a point which is, say, 1 plus epsilon time within the radius of 1 plus epsilon times to the closest distance to the closest point of the query point. Right? So you can think of this. This is kind of some tolerance uh, in the answer, and then we'll see that this approximate similarity search can be solved in sublinear time with provable guarantee. Okay, so here in this case, its time is linear. So we'll try to improve it to sublinear, to give a query time which is sublinear in n, and we'll see that its space is much smaller than this. Right. So this is what we are going to do today.
But the time will be same as.
The time will be sublinear. So sublinear means like small of n. It could be running time will be asymptotically smaller than the linear.
What I mean to say, the other one was n in d into log n, right? So whether
So
it will be lesser than.
So by choosing the parameter, it could be smaller than this, but certainly like here, in this case, in order to get sublinear time, we are paying a price in terms of space, right? So we'll see that we don't have to pay that much of price in terms of space, and still we can get a sublinear time algorithm. Right. So in our we'll see that in running time there are parameters, and we can carefully choose the value of the parameter, and we can get a trade-off between query time and space. Right?
Okay, sir.
Okay. Okay, but before that, we'll see another version of the problem, and we'll see that approximate nearest neighbor search problem can be solved using the problem that we are going to define. Okay, so let's define one more variation of this problem, that is called approximate near neighbor problem. Okay, again here we have given a set X of objects, given accuracy parameter epsilon, and we have given another one more parameter, which is distance threshold R. So these two things are given to us offline, and we have given like a query object Q at the query time. Right? And these are our input, and our output should be basically find an object Z again that is most similar to Q, such that, okay, so here now we are going to define like what should be the answer, what should be the output of the algorithm. So if there is an object Y in X such that distance of Q to Y is at most R. So basically, if there exists a point Y in our data set such that distance of Q to Y is at most R, then basically we can return an object Z that is distance at most 1 plus epsilon times into R. Right? Then return object Z in X such that distance of Q to Z is at most 1 plus epsilon times into R. Okay. And if there is no object, there doesn't exist any object such that distance of Q to Y is most 1 plus epsilon times R, then just return no. Okay. Okay, so I'll just try to, whatever I have written, I'll just try to illustrate it with following example. Okay, so suppose this is our query point. Okay, so suppose this is okay. So the first point says that if there exists a data point y such that distance from q to y is at most r. So suppose this is, in this case, we have a point y. So suppose this is a point y that is within the radius of distance r from the query point. So suppose this is our query point. Then algorithm can output any points that is distance at most 1 plus epsilon times into r, right? So then algorithm can output either this point or this point or this point or this point, or in fact it can output also y as well, right? So basically if there exists a point that is within the distance r from q, then algorithm can output any point in the radius of 1 plus epsilon times into r from q, right? And if there doesn't exist any object from at distance 1 plus epsilon times r from q, then algorithm will just output no. Right. So is the problem setting clear? So it might be a bit subtle. So just I'll take a pause and just let me know if you have any questions on this.
Accuracy parameter epsilon and L distance threshold R. So what is that
Sorry?
L distance? So in the second point, right?
Huh?
It is mentioned that given accuracy parameter epsilon and L distance threshold R. What is that L distance?
L, where is L? I don't see any L.
Oh, that's a bracket or something. The second point.
So in
Then,
the input one where you have defined L distance.
oh, that is and
And okay.
the distance threshold R.
So one quick question, like
Yes.
you're saying that it will output any one out of this which is inside circle, right? How
Yes.
it will decide?
No, like as long as any of these points are outputted, we are fine. And how, which point will be outputted, we'll see that in the algorithm. Right. So far, we have just formalized. We are trying to formalize the problem. We have not discussed anything yet about the algorithm.
Okay, got it.
So first, we are formalizing the problem. Once we are through with the problem statement, then we'll see the algorithm.
So basically here we are saying it will return only one object or none, right?
Yes, yes. One, if this condition is satisfied, and it will return none if this condition is satisfied.
So shouldn't it be greater than 1 plus epsilon? The second point.
No, I'm talking about distance. So
So the second point basically means if it's outside the 1 plus epsilon and radius, then we should return no, right?
yes. Basically, the second point says that if there is not any point within the radius 1 plus epsilon times r from q, then algorithm will say that there is no similar point, like there is no similar point to q.
Okay, okay, okay.
Okay, so okay,
So one question.
yeah.
So little bit confused with this problem and the other problem, the last problem.
So I'm going to revise it. Okay.
Yeah, yeah.
So we started with the problem of exact nearest neighbor search problem, and we saw that either if Like either if we get linear time algorithm, then the space is somewhat controlled. But if you are getting the faster algorithm, then the space complexity is high. Then we saw, okay, we'll not worry too much about the exact nearest neighbor search problem. We are happy with if we get the approximate solution. So how to the approximation error in approximation is defined as the follows. Like in this setting, we have again endpoints in d-dimensional space as input and parameter epsilon uh, given to us offline, and we have given a query object queue at the runtime. So here, so our aim is to output a data point z that is most similar to q, such that, so suppose if say x is the closest point to q, then our algorithm should output a point that is distance 1 plus epsilon times uh, 1 plus epsilon times distance from x1 to q. Right? So say suppose if say x1 is the closest point, then, and this is 1 plus epsilon times distance of q, then algorithm can output any of these points, either this or this. Right? And
Sir,
here, yeah,
so a nearest neighbor is a
nearest.
subclass of the near neighbor problem, right? Is a sub
So
problem of,
no,
can
it's
we think of it
other
like
way
that?
around. So in
Okay.
this problem, we are introducing one more parameter r. Right? So this is more generic problem. Approximate nearest neighbor is more generic problem, and in this problem we are putting one more constraint. One more, we are introducing one more parameter epsilon. Distance threshold r. Right? And then we'll see that if we can solve this problem, approximate near neighbor problem, efficiently, then we can also solve this approximate nearest neighbor problem. Okay. Okay. So here we introduce one more parameter, distance threshold. So again, our aim is to find an object z that is most similar to q in the following sense. So if there exists an object y from y in x such that distance from q to y is at most r, then we can return, algorithm can return uh, any point that are distance 1 plus epsilon times uh, r. Right? And if doesn't exist any object y such that distance from q to y uh, is 1 plus epsilon times r, then algorithm can say, okay, no, there is no similar point to q. Okay, so now the thing is, so using approximate near neighbor problem, will solve approximate nearest neighbor problem. So what I mean, like if we have any algorithm that can solve this problem, approximate near neighbor problem, then calling that algorithm multiple times, we can solve approximate nearest neighbor problem. We can solve this problem. So
So
any idea?
if we set r equal to 1, it's the same.
Hmm.
It'll nearest neighbor will become near neighbor, right? Sorry, the other near neighbor will become nearest neighbor, right?
Not really, because we don't know how this r is related with the distance of x to its closest point, right? that we don't have any control with. Okay, so here here we have distance of x1 to q, where x1 is the closest point to q, and here r is some parameter, and we don't know the distance of x1 to q a priori. Otherwise, there is no point of running like designing an algorithm. Like if we already know like which point is closest to q, then we don't need to do anything, right? So
Sir, that's mean we are assuming R, right?
Yes.
We are assuming R as a nearest point, like the distance of the nearest point.
No, here there is no assumption on R. So R is part of input.
Okay.
So how we can choose R? Like what is the range of R?
Yes, yes. So any guess what could be the range of R so that we can solve this problem? Approximate nearest neighbor search problem. Right. So you are on right track. We basically we need to run this approximate near neighbor algorithm by choosing R carefully. Right. So what could be the possible range in which we can choose R carefully?
Be some epsilon times lesser than distance of this thing plus
Right.
some
So
extra.
yes, so you are on right track. Okay. Okay, very good. So basically, yes, you are on right track. So we'll use the algorithm that can solve this approximate near neighbor problem as a subroutine and try it out for different values of R. Okay, and how we'll do it? I'm just going to elaborate it. So suppose we have some information about the input, right? So suppose we know what is the closest pairwise distance and what is the largest pairwise distance, right? So suppose we have this information with us. Okay, so let d and so not d, maybe I should use some other d prime and d are smallest and largest pairwise distance. What do I mean by this? Like, so distance, the closest distance between any pair of point in the data set is d prime, and the largest distance between any pair of point is say capital D. Okay.
Sir, one
Then
question.
yes.
In the approximate near neighbor problem,
Hmm.
can you scroll one line?
Yes.
Yeah, here. So we are saying if there is an object y is belonging to x such that the distance of q and y is less than equal to r, then
Yes.
return the object z such that
Hmm.
distance between q and z is less than 1 plus epsilon r.
Hmm.
And the other condition is distance between q and y less than equal to 1 plus epsilon into r. The no condition,
No, no. Yes.
the
Yes.
second. So what about the points between like 1 plus epsilon r and r, that region where
So in which case?
in the so
First
the
case or
yes,
second case?
the
Yes.
first case, the distance
Hmm.
condition is between q and y less than equal to r. We know what to do. And the
Hmm.
second case is 1 plus epsilon into r. We know what to do, right?
Yes.
What about the region in between? So we just
So in between that region, like we
that is
don't.
epsilon r.
So in that case, we cannot say anything.
Okay.
Okay, so this is the way we are formulating the problem so that we can solve this problem efficiently.
Okay. Okay.
Like if we, so that's why, so that is the region where algorithm can make error and we don't have any control on that.
Okay.
Otherwise, if we can solve all these three conditions, then essentially this is solving nearest neighbor problem, exact nearest neighbor problem, right? So again, we'll
Okay.
be in a linear time algorithm kind of setting. Okay. So that's a good point. Okay. So yeah. So now suppose we have information about uh, like smallest and largest pairwise distance in the data set. Then can you help me choosing the like how we can choose R so that we can solve our approximate nearest neighbor problem? We need to set R as what? Like we'll start, we set R as say D prime first, 1 plus epsilon times D primes, 1 plus epsilon square D prime, and so on. Right? And so basically the idea is, so try different values of R and the values will be gradually increasing. Right? So since D prime is the smallest pairwise distance, we can choose R as a D prime. And we run, so, and suppose we have some algorithm to solve this approximate neighbor problem. We'll run this algorithm with say value R is equal to D prime. If we get a point, well and good, we'll stop. If we didn't get any point, we'll try R as 1 plus epsilon time D prime. If we get a point, we'll stop. Otherwise, we'll try different values of R and so on, right? So we need not to try indefinitely because there is a point at which we have to stop, right? Because that is D. So is this point clear?
So why we are choosing 1 plus epsilon square then cube? Is it for some computation, or since we are saying epsilon will be very small value, so squaring is like, I just wanted to know the reason of
So basically we
squaring.
want to try different values of R so that are gradually increasing.
I mean, one can try like 1 plus 2 epsilon, 2 square epsilon, that kind of, I mean, any pattern is possible, right?
Yes. So, and also so that the number of times that we need to uh, do this iteration is also not very large.
I see. Okay.
Right. So basically in a way, so suppose, so first you are trying with this region, then you are trying with this region, then you are trying with this value of R and so on, and you are increasing it. Right. So if we,
Okay.
and he, so how many iteration we need to do? So this you can see that we are forming a what geometric series.
Yes.
And how many terms will be there? So that will determine the number of iteration. Iteration that are number of elements. This will be order of log d upon d 1 plus epsilon. So this you can verify it using the formula of geometric series. Right. And again, as I said, our algorithm will be run algorithm for, which is this problem, approximate near neighbor. Using different values of R and basically different values of R that are gradually increasing and return a point as soon as we get it. And stop. Right. Okay. So we'll see that how this approximate nearest neighbor near neighbor problem can be solved using a very popular algorithm called locality sensitive hashing. And if we can solve this approximate near neighbor, then by doing this the standard trick, we can solve approximate nearest neighbor as well, right? So we'll see algorithm to solve approximate near neighbor is locality sensitive hashing. LSH. Have you heard about this algorithm before?
Yes, sir. Actually, in data mining, we have covered this.
Data mining course in
Yeah.
in your MDS program.
Yes.
Yeah.
Okay, fine.
But it will be good if you explain it once again as well. In terms of
Okay,
this.
sure. Anyway, I'm going to explain it.
Yeah.
Okay. Okay, so the idea of this algorithm is very simple and intuitive. So so here basically we need to, the aim is to design a kind of functions that maps similar point. So basically here you can think of, so suppose we have, these are our data points, say maybe so suppose these are our data points. And we want to like solve this approximate near neighbor problem, right? So the main challenge here that we don't want to compare the query item with all the endpoints in the data set, right? So the idea of locality sensitive hashing function is to group basically these group points into different buckets. So basically, suppose you can think of, we are designing different buckets. Okay. And it should be such that the similar point should go into the same bucket with high probability, and dissimilar point should go into different bucket with high probability. Okay. So for example, so say these 2 points are mapped over here. Right? So, and for example, these 3 points are similar. This, like this, and this, and this could be maybe here. And suppose we have one more bucket, in which the last point goes. So basically, look, here the idea is grouping the points into different buckets with the guarantee that with high probability, similar point will go into the same bucket, and with very small probability, different point will go into the same bucket, right? So essentially, now what we need to do, we need to come up with a kind of mapping, right? So suppose these are our buckets, and we need to map these points to these one of these buckets. So these are buckets, and we need to design a mapping to map data points to different buckets, right? So is this point clear? And the constraint is similar points should go to same bucket, and not so similar point should not go into the same bucket. Right? So does this make sense?
So what is the definition of similar points, on which basis we have decided? That is again previous algorithm?
Yes, so it's depend on the data type. So data type and the similarity measures. So suppose it could be, say, real valued vector and cosine similarity. So if the so basically depending on different data type and similarity measures, this can be designed. But for simplicity, you can think of our data points are real valued vector, and similarity, like similarity or distance, we are computing as, say, Euclidean distance. Like, so we are saying a point is similar if the Euclidean distance is small. Right? So does this make sense?
Yeah.
Okay.
Yes, sir.
So any idea like why we are doing this and how this can help us to get sublinear algorithm for approximate near neighbor problem?
Probably this will help us in reducing the search space.
Yes, and how it is helping us to reduce the search space? That's correct.
Yeah, so basically because of this similarity logic, right? Like we are identifying this and going to the bucket, and now our target will be like, after we find out, we'll just check that bucket data only.
Yes, that's correct. So basically we have, suppose we have some mapping which maps similar point into the same bucket with high probability. Then essentially now we have group of points, like buckets that consist of some subsets of points that are highly similar. And now once we get the query point, say suppose this is our query point, say Q, we'll see in which bucket that Q is falling. So for example, suppose if Q is falling into this bucket, then we need to compute the distance of Q with only those points that are in this bucket, right? We don't need to care about the points that are in this bucket, or this bucket, or maybe if there are some other buckets and so on. Right. So our search space is limited to this bucket only. Right. And we'll see like how LSH could help us in designing one such mapping, which gives us sublinear time search algorithm. Okay, so now I'd formally state the LSH. Yes.
Sir, here how do we decide the number of buckets?
Yeah, so we'll see all those things in detail. Yeah. So basically the number of buckets, and there are other things that determines our runtime complexity and other trade-off with basically space and so on. So that we'll see in later, in later part today. Just for now, I'm just giving you a high-level idea.
Okay.
Okay. So here basically the problems boils down to finding a hash function or function which satisfies this property, right? And locality sensitive hashing gives one such hash function for the same, right? So I'll state so if family of functions is called. So now I'll be more precise. So here so in this example, I was just stating like this hash function maps similar point into the same bucket with high probability, and not so similar point in the same bucket with very small probability. Now I'll be formally stating this thing. It's called SCS, C is parameter, C into S, P1, P2 sensitive if for any two objects X and Y, if similarity of X and Y is more than S, or alternatively distance of X and Y is at most S, then probability that their hash value is same, that Hx is equal to Hy is same, is at most P1, and similarity of X comma Y is at most C times S, or equivalently distance of X comma Y more than C times S, then probability that Hx is equal to Hy is at most P2. And C is some parameter smaller than N, and P1 is much greater than P2. Right, so you can think of P1 is say 0.995, and P2 is say 0.05, and so on. And this probability is over selecting hash function H from the family F, right? Okay, so basically a family of functions. So F is a family of hash functions that consist of H, say, right? It's called SCS P1 P2 sensitive if we take any two objects such that, so here we are like precisely stating if the points are similar, if their similarity is more than S, then probability that Hx is equal to Hy, basically the hash value of both X and Y will be same, will be probability at least P1. And if similarity of X and Y is at most C times S, then probability that their hash value is same is at most P2. And P1 is much larger than P2. Right. So is this definition clear?
Here we are checking for each object the similarity, right? So basically, if I have 100 objects, so it will be 100 C2.
No. So here I'm just defining hash function, like LSH hash functions. And so far we have not like come up with any algorithm. So far I'm just
Okay.
defining a like locality sensitive hash function and the property of locality sensitive hash functions, and then we'll see how we can use this locality sensitive hash functions for our approximate nearest neighbor problem. So this is just for definition. We are saying that we call a function family of hash function F as locality sensitive hashing, like SCS P1 P2 sensitive, if it satisfies the following two criteria. Right, and then we'll see how we can come up with such LSH, locality sensitive hash functions, and then we'll see how we can use it to solve our approximate nearest neighbor search problem.
Okay, and C here is a constant and S is also a constant, right?
Yes, so these are parameters given to us.
Okay.
Any questions so far?
Sir, here S is defined as similarity xy greater than equal to S or distance xy less than equal to S. Sir, how we compare similarity and distance with the S? Like either
No. So here just this is a generic framework. So think of like it can be defined in two ways. Like although both of them are equivalent. So if it's saying, so this line is saying that if similarity of point is high, at least S, then probability that their hash value of X and Y should be same uh, with probability at least P1. Or similarity and distance are kind of complement to each other. Like if similarity is high or distance is small.
so we can use either of this, right?
Either of this. So in some reference, you can see this is defined in terms of similarity, and in some reference, you can see that this is defined in terms of distance. So I'm just writing both of them as they are equivalent.
Yes, sir.
Okay, so we have seen one LSH algorithm in our class. So can you recall which LSH algorithm we have seen? Okay, so I think we can take a break now, and meantime, just do brainstorming. In our last few classes, we have seen one LSH algorithm, LSH hash function. So just think of which LSH algorithm we have seen, and I think we'll meet at 11:30 sharp. Okay, so I'll stop here now.